Throughout this training, or at any time you need support, there are many ways to contact us. You can follow us on all major social media platforms or email us directly via our website, or you can click the Cancel Connect icon shown at the bottom of this slide on our website to book a consultation with one of our experts.
Now, before we go further with your own project and the measure phase, we're going to cover some foundational concepts of statistics and measures. Once you understand it, there's nothing boring about statistics and measures. Really? And it's not only for experts, but all of us can benefit from understanding the stories in the numbers. There's so much data around us, but on its own, data is really just noise and confusion. To find the meaning in the data, we need to understand statistics.
So instead of wasting our time making decisions based on gut feeling, guesses, prejudice, and assumptions, our eyes and our minds can be open to fact-based views of the world around us. This makes statistics one of the most exciting subjects around. Yes, it's true.
I know.
In this module, we'll give an overview of a few foundational points in the world of statistics and continuous improvement.
Understanding the basics of statistics makes you a better informed contributor and will strengthen your ability to accurately evaluate situations that affect you. Statistical literacy is a critical component of creating real improvements.
We're not statisticians. Our specialty is business improvement. But as continuous improvement professionals, we spend a lot of time trying to understand patterns in piles and piles of data. We have to have reliable methods to determine whether what we think is meaningful really is. That's when we turn to statistics to tell us whether the things we think or believe are actually true.
For us, understanding the basics of statistics is essential for our work. But it's not just for black belts or master black belts. Statistics is vital to people at all levels of industries such as banking, healthcare, manufacturing, agriculture, politics, etc. Understanding the basics of statistics will provide you with a strong foundation for understanding data that you can get bombarded with in your everyday life. Just paying attention to the news or to reports at work, it's important to determine whether the claims in a chart or graph are reasonable. Does what you see in the chart make sense?
Statistics is a branch of mathematics that deals with the collection, analysis, interpretation, and presentation of numerical data. The word may make you think of polls and surveys or facts and figures in a news article, but statistics is more than just a bunch of numbers. It's a problem-solving process that seeks answers to questions through data. That's why it's so importantly linked to Lean 6 Sigma and process improvement.
By asking and understanding statistical questions, you can learn more about the world around us. Statistics is used every day to help us gain insight into questions that affect our lives. Is our customer population growing or shrinking? What is the safest way to increase our productivity? Will eating more fruits and vegetables really make us live longer? The practice of statistics is like most things. The more you use it, the better you get at it. And it's best learning by doing.
Statistics always begins with a question. How many calories are in a hot dog? How long does it take to admit a patient into the emergency department? How much of our beer will evaporate in the next 30 days? What's the average boot size of an American soldier? In the define phase, we identified a specific problem. And here in the measure phase, our question is, how big or bad is that current problem? And what data do we need to understand the causes?
So Claire, what do you think about this idea that it all starts with a question? I mean, in your experience, do you think that most people understand this about data?
I really don't. I think most people gather the information that's always been presented to them. They look at the same reports, they look at the key data that has always come up without really thinking about what question am I trying to answer? And that's what we're trying to teach with statistics is first develop the question. That's where it starts. Now build your plan from there. So before we start looking at specific measures, let's understand about data in general.
Qualitative data is descriptive. This data may contain descriptive phrases and opinions. Examples include an online review a customer writes about a product, an answer to an open-ended survey question about what type of video a customer likes to watch online, and the conversation a customer had with a customer service representative. Qualitative data helps explain the why behind the information. For this reason, it is useful for supplementing quantitative data, which will form the foundation of your data analysis.
Quantitative data comes in the form of numbers, quantities, and values. It describes things in concrete and easily measurable terms. Examples include the number of customers who bought a given product, the rating a customer gave a product out of 5 stars, or the amount of time a visitor spent on your website. Because quantitative data is numeric and measurable, it lends itself well to analytics. So we can study this car and we can gather descriptions of this car and might find characteristics such as
Awesome!
It's really fast, it's really expensive, it's luxurious, and it's a best-selling car. Those are qualitative descriptors.
Or we can gather some information about this car and say that it goes from 0 to 100 in 2.5 seconds. It seats 5 adults. It weighs 2,316 kilograms. It has 804 liters of cargo space. These are quantitative measures, and quantitative measures have 2 types.
So let's say you're a parent, and your young child wakes you up in the middle of the night complaining that they don't feel good. What might be the first thing you do? Maybe you'd lay your palm on her forehead. And what are you doing that for? Well, you're taking a measurement with your hand and you're checking to see if the child feels hot or not hot. If the child feels hot, then you'd likely get a thermometer to determine precisely how hot the child is. This simple example illustrates 2 different types of data, discrete and continuous.
So discrete data, also called attribute data, is a count, proportion, or percentage of a characteristic or category. So we could check a whole group of kids with a hand-on-forehead method and count how many felt feverish and how many did not. Or we could take that same information and say what proportion of kids felt feverish. The key with discrete data is to clearly define the categories. When we use the thermometer, this is an example of continuous data. Continuous data is any variable measure on a continuum or scale that can be infinitely divided.
Continuous data uses a system or an instrument such as a ruler, a scale, a clock, a monetary system, and it measures factors such as cycle time, cost, revenue, dollars, weight of a package, length of a piece of wood. Measures of continuous data can be broken down into further detail if needed. For example, we can measure time using hours, or we can measure it using seconds, just depending on what we need and the instrument that we have.
Discrete data is just data that cannot be broken down into smaller parts. This type of data counts categories, attributes, or characteristics, and is required definition of these categories or attributes. Some examples of discrete data might be the types of tree, number of members in the region, proportion of defects, or customer type.
In your workbooks, you'll find an exercise to see if you can distinguish the type of data for a bunch of sample metrics. Pause the video now to test your understanding. We'll come back and review your answers.
Go! Okay, so let's see how you did. We'll cover the continuous measures first. Operational costs, time to check into a hotel, weight of a box, height of a tree are all continuous. They each use some type of an instrument or scale to complete the measure.
And they can be infinitely divided, meaning that we can get more and more granular with a more sophisticated instrument. Now for the discrete measures. Sales region, customer category, breed of dog, color of hair, you probably got those right. The trickier ones to recognize as discrete are proportion defective, income level, and count of defects. Proportion and count usually throw people off because it's a continuum of numbers. However, what we're measuring is the proportion or count of a category. So, for proportion defective, for example, we're counting the categories of defective or not defective. Counts and proportions are always discrete.
Better be discrete. You might wonder why the type of data matters, but it becomes quite important when you are ready to display your data on a chart. Certain charts require certain types of data. For example, height on a histogram requires continuous data. Categories of defects on a Pareto chart requires discrete data. We'll learn more about these charts shortly.
Decisions on what to measure should take into account the type of data that you can collect. One of the most important considerations involves the option of taking continuous or discrete measures. Of these two types, continuous is usually preferable. Advantages include the ability to draw conclusions from smaller sample sizes and to perform a more robust statistical analysis.
Something to consider with these data types is that if you gather continuous data, it can be simplified to groupings or categories that make it behave like discrete data.
Do you have an example?
Well, using our fever example, if we took the temperature of 100 children, we could take that specific temperature data and break it down into two categories, fever and no fever. Or if we measured the amount of time it took for our pizzas to be delivered, we could categorize the deliveries as late or not late,
Okay.
or free. But we can't go the other way around. If we gather discrete data, when we're collecting our measures, for example, we track late and not late. We can't take that data and convert it to actual delivery time.
Now, time to learn about some helpful measures.
Yay!
One of our objectives in this phase is to determine the best way to measure our baseline. In this section, we'll review some common baseline measures used in Lean Six Sigma. You may be familiar with some of these calculations and others might be totally new to you. We'll cover defects per unit, defects per million opportunities, the sigma level of process capability, percent defective, final yield, first pass yield, rolled throughput yield, average, and variation.
Before we get into the measures, let's clarify a few important definitions. Unit is an item being processed or a service being provided or the final product or service being delivered to a customer. Defect is any failure to meet a requirement or standard. Defective unit is a unit that contains one or more defects. Defect opportunities are the number of ways unit can fail to meet requirements.
So in our example here, the unit is the phone. There are 4 defect opportunities, meaning that these are likely defects that can occur on the phone. A defect is any one of these situations: a cracked screen, Wi-Fi won't connect, water damage, or the unit won't charge. A defective unit is a phone with one or more of these defects. Get it?
I think everyone gets the phone example. A defect is defined as anything outside of customer specifications. In other words, a defect means any event or transaction that does not meet the customer requirement. A defect should also be thought of as a failure to meet the customer expectations for quality. In our example here, we have 6 phones. Of the 6 phones, there are a total of 6 defects. Working the calculation of total defects divided by total units, we get a DPU of 1 or 1 defect per unit. Easy.
So DPU is a good measure to use when the goal of the project is to reduce defects. After all, that's the main reason why we use the structure of Six Sigma. to reduce variation and defects that impact our customer, the employees, and ultimately the business.
Try this calculation yourself. In your workbook is an example for you to calculate defects per unit, DPU, for a website application form. Each computer screen is a unit. A red X indicates a defect.
Rian, before they pause the video, is it important for them to do these practice activities as part of the training?
Well, I think it's really important to practice because practicing makes everything easier, as we said earlier. But if you choose not to, and that might become a problem later on.
Yeah, the thing is, it makes sense as we're speaking it and you're looking at the math and DPU, you get it. But as a green belt, you need to know these things off the top of your head and be able to draw on them and know when to use them. So practicing them and just taking the time to write it down with your pen right on the paper will help solidify it a bit more. So pause the video now so you can work on this calculation. Defects per million opportunities is a pretty interesting measure and is commonly used in process improvement projects. This measure is based upon first defining how many opportunities there are for a defect in a product or service, a type of potential defect on a unit of throughput that impacts a customer requirement. The DPMO measure adds the dimension of opportunities to the defect equation. By including opportunities, that is, chances or types of errors, we can compare defects across different types of processes with varying levels of complexity.
The key to using this measure is to determine how many opportunities exist on a single unit going through the process. In our phone example, we have defined that there are 4 opportunities for error on each phone: cracked screen, Wi-Fi won't connect, water damage, which never happens, and phone won't charge. Defining the defect opportunities is not an exact science, but there are a few rules of thumb that you can follow.
So the rules of thumb. First, a defect in a product or service is defined as any time we failed to meet a requirement. So this is not an internally focused measure. Second, we have to be reasonable in how we're counting defects. For example, with our phones, we have said that a cracked screen is one defect opportunity. We don't separate it to say, well, we could have a defect on the top portion of the front screen, the middle or the bottom portion of the screen. We grouped cracked screen together as one potential defect. Same concept on a form, for example. We'd say that incorrect address is one opportunity for a defect. We don't count the street number, the street name, the city, the state, the country, the zip code as 6 different opportunities. If you do that, it really throws off the calculation.
Thirdly, when we are using DPMO in multiple processes, it's important to keep a similar granularity when defining defects. Otherwise, our comparison from one process to another does not work. DPMO is a decent measure to use when we want to compare the performance of multiple processes, especially when they have different levels of complexity. The more complicated a process, typically the more opportunities for error. And using DPMO gives us a better way to compare apples to apples.
In our example here, we have 6 defects and 6 units. Each unit has 4 defect opportunities. So 6 defects divided by 24 opportunities times 1 million gives us 250,000 defects per million opportunities.
So in your workbook, on the top half of the page, there's an example for you to calculate defects per million opportunities, DPMO, for our website application form. Each computer screen is a unit. The red X indicates a defect, and each unit has 5 opportunities for a defect.
On the bottom portion of the page is another example from the same business. This example is for you to calculate DPMO for the production process that makes the products ordered on our website. This unit is the little box. A red X indicates the defects. Each unit has 2 opportunities for defect. Compare the two processes from the same business to see which has the better quality. Pause the video now so you can work out the calculation.
Pause. Final yield measures the total number of defect-free units out of the total number of inputs. It represents the acceptable pieces at the end of the process divided by the pieces started. Final yield is a good measure to use to understand quality from the customer's perspective. Focus on quality and effectiveness of our process. In our example here, we have our 6 units. Of the 6 units, 3 came out defect-free, and 3 divided by 6 gives us a Y final of 50%.
In your workbook is an example for you to calculate final yield. Review the SIPOC of the call center process. Now review the number of calls received and the number of calls successfully resolved to calculate the final yield. Pause the video now so you can work out the calculation. If you know how to calculate DPMO and final yield, which you do, you can actually back into the sigma level. There are a few ways to derive sigma level of a process, and using the calculated DPMO or the final yield are 2 ways. The table here shows the corresponding DPMO and final yields for 1, 2, 3, 4, 5, and 6 sigma.
Finally, a little bit of a simple chart to explain 6 Sigma. It's not as complicated as what everyone thinks it is. You'll notice that when you get above 3 Sigma, the final yield is all above 99%. A lot of organizations believe that 99% quality is good enough, but that's not a solid assumption. Looking at the DPMO gives us an idea of the difference in the customer experience or quality of the output between 99.3 and 99.99%.
We do a lot of work in healthcare. If 99% was good enough, 12 newborn babies will be given to the wrong parents every day. 20,000 incorrect drug prescriptions will be written this year, and 291 pacemaker operations will be performed incorrectly every day.
Not sure that's a good thing. And with our banking customers, if 99% was good enough, 880,000 debit cards in circulation will turn out to have incorrect information on their magnetic strips. We don't always have to aim for a 6 Sigma process, but the important thing is to understand what is the right target for our process, given the impact of our quality on the customer and on the business.
Sigma level is a good measure to use to establish consistent measures within an organization. Just like DPMO, it allows you to compare processes that are vastly different with a single measure.
In your workbook is a segment of the full-blown Sigma conversion table. Use that segment of the table to determine the Sigma level for the call center process. Pause the video now and fill in the Sigma level.
A defective unit is any unit that has 1 or more defects. Proportion defective is the opposite of final yield. If the final yield is 70%, the proportion defective is
30.
Good job. Proportion defective is a good measure to use when specific count of defects is not as important as a defective unit versus a good unit. In other words, it doesn't matter whether a unit has 1 defect or 5. In the customer's eyes, the unit's defective.
For example, if you ordered a nice glass of wine from a restaurant and there's a big lipstick print on your glass, it doesn't really matter if there's 1 or 2. It's defective, and that's all that matters. In this example here, we have 6 total units. 3 of the units are defective with 1 or more defects. Doing the calculation, total number of defective units divided by the total number of units gives us a 50% proportion defective.
In your workbook is a graphic of a process that starts at a factory. The factory delivers raw ingredients to the business. The business goes through their process to turn those raw ingredients into bottled vitamins that get delivered to their customers. In this example, of 1,700 jars that were produced, 57 were defective. Pause the video now to do the calculation.
Once we know that our process is meeting customer requirements, in other words, the final yield or proportion defective is good, then we can focus on our internal efficiencies. That's when we might use the first pass yield as a measure.
While the final yield measures how many good units were produced, the first pass yield looks at how many were produced right the first time without having to be corrected or fixed along the way before it went to the customer. This measure accounts for all the fixes, the rework, the inspections, the corrections that happen within a process to catch defects or mistakes before it gets to a customer. These are the necessary efforts of the employees to make sure that our product or service is high quality, but it's very costly to the business. Our goal is to serve our customers profitably, and to do this, we have to pay attention to the costs of our process.
In our example, we see 3 phones with black X's. That indicates that there was a defect that was caught before the unit was sent to the customer. So the number of phones that were produced right the first time with no defects along the way is 2. 2 divided by 6 gives us a first pass yield of 33%.
That's really low. In a service process, let's say we're at the gate and ready to board a flight. The gate agent recognizes that there are 2 people assigned to your seat. Without you knowing what he or she is doing on the computer, the error is being fixed so that by the time you arrive at your seat, the problem has been resolved. If we were using final yield, we would not catch that this error even occurred, as we're only concerned with those defects that actually reach the customer. So if you arrived at your seat and someone was actually already sitting there. Our goal in a process improvement project is to understand how the mistake happened to begin with, and to avoid using up the gate agent's time fixing errors. If the error hadn't occurred to begin with, the customer wait time and throughput at the gate would have been improved.
So first pass yield is great to use when internal costs and efficiencies are the focus. In your workbooks, let's go back to our vitamin manufacturing process. We calculated the final yield on the top of your workbook page. Now let's take a look at the efficiency of the process and see how much rework is going on where the work is happening. Pause the video now to calculate the first pass yield.
A measure of central tendency is a single value that attempts to describe a set of data by identifying the center position or central location within that set of data. The average, often called the mean, is most likely the measure of central tendency that you're most familiar with, but there are others, such as the median and the mode.
A simple example here to calculate the average. Using our phone example, we have 26 units and we are measuring the average battery life when constantly streaming videos. Add up the total and we get 120 and divide by the number of units for an average of 4.61 hours of battery life. The mean, median, and mode are all valid measures of central tendency, but under different conditions, some measures of central tendency become more appropriate to use than others. You can always use both of them, one metric to calculate the average and another the median. This lets you see which measure will be most useful in a particular case. However, understanding these terms will make it easier to choose the right measure for your project.
The average and the median play a similar role in understanding the central tendency of a set of numbers. Average has traditionally been a popular measure of the middle point in a set of data, but it does have disadvantages of being influenced by a single value, which is much higher or lower than the rest of the values. That's why the median is a better midpoint measure for cases where a small number of outliers could drastically skew the average. If the data you're comparing is mostly uniform, then you can safely use the average. However, if your number set has some highs or lows, some outliers, then you might want to consider using the median to filter out the values that are skewing the results.
So while this is a measure of the central tendency, what's the problem with averages? They hide the spread. And the average isn't always the most useful measure on its own if you don't have the insight into the range or the spread of the values. If you think about it, on average, people have slightly less than 2 legs. Oh dear. Almost everyone has more than the average number of legs. Some people have less. No one has 3. Well, not that I know about. Let's take a closer look at variation.
The range of a set of data is the difference between the highest and the lowest values in the data set. To find the range, first order the data from least to greatest, then subtract the smallest value from the largest value in the set. You can see in the example here that we have ordered the battery life of our 26 phones from how high and subtracted the lowest value from the highest. This gives us a range of 5.5.
In statistics and mathematics, the range provides one way to understand how varied the data set is. 2 important features of a data set include the center of the data, as we discussed previously, and the spread of the data. Similar to the central tendency, there are different ways to calculate how spread out the data set is, and the easiest and crudest measure of spread is the range.
So the range is a crude measurement of the spread of the data because it's extremely sensitive to outliers, and as a result, there are certain limitations to the utility of a true range of a data set because a single data value can greatly affect the value of the range.
For example, consider this set of data here. The maximum value is 7, the minimum is 2.5, and the range is 5.5. Then consider the same set of data, only with the value 100 included. The range now becomes 100 minus 2.5, which is equal to 97.5. The addition of a single extra data point greatly affected the value of the range. There are more complicated ways to understand the spread, such as standard deviation, but the drawback is the calculation is more complicated.
So when should we use the range? The range is a good way to get a very basic understanding of how spread out the numbers in the data set really are, because it's easy to calculate, as it only requires a basic mathematical operation. We can use some nice data display tools to visualize the range of a set of data. The dot plot, the box plot, and the histogram visually summarize the hours of battery life for our 26 cell phones constantly streaming video.
Say that again. The dot plot, the box plot, and the histogram.
Another way to measure variation is to calculate the variance. The variance is defined as the average of the squared differences from the mean.
Wow, let's say that again. That's a little bit complicated.
All right. The variance is defined as the average, so we know how to do an average, but instead of doing the individual data points, we're averaging the squared distance or difference from each data point to the mean. So what's the average distance from each data point to the mean? So to calculate the variance, first we calculate the average, then for each number, we subtract the average or the mean and square the result. That's the squared difference.
Feel free to pause the video at any time if you don't get this and rewind and listen to it again.
Once we've done that, we work out the average of those squared differences. You might ask, why are we squaring them? And all we'll say at this point is because math. In Excel, calculating variance is really similar to calculating standard deviation. Ensure that your data is in a single range of cells. If your data represents the entire population, enter the formula, as we have here in orange on the screen, equals var.p, and then in parentheses the range of data. Alternatively, if your data set is a sample from a larger population, enter the formula equals VAR. So you'll notice, and we'll get into this a little bit further in the measure phase, is that we treat our sample data a little bit differently than we do when we're studying an entire population. So this is here for your reference. You don't have to commit this to memory, but just know that it exists.
Excellent. Standard deviation is represented by the Greek letter for sigma. The standard deviation is a measure of how spread out numbers are. The formula is easy now that we understand variance. Standard deviation is the square root of the variance. Use the Excel formula as shown here, equal to STDEV, and select the range of values which contain the data. This calculates the sample standard deviation. The standard deviation is always in the same units as the measure. So in our example, we are measuring hours of battery life. The standard deviation of 1.26 says that the average distance of each phone from the average is 1.26 hours. The higher the standard deviation, the wider the spread of data.
Now we'll get deeper into understanding the distribution or the spread of our data and our standard deviation. In this example, we have a histogram that's measuring the time to process an order, and it's stated in hours. The average or the mean of this data set is 4.61 hours. The standard deviation is 1.26 hours. Let's first use this data to illustrate the standard deviation. The normal distribution is that bell curve that you may remember from school. Normally distributed data means that the majority of the data is clustered around the center with less and less data to the left and to the right.
Knowing the mean and the standard deviation gives us a lot of insight into our data. No matter the specific number or spread of the data set, we can predict that about 68% of the data will fall between plus or minus 1 standard deviation from the mean. So 68% of our phones will have battery life between 3.35 and 5.87 hours. 95% of our phones will have a battery life between 2.09 and 7.13 hours. And we can predict that we're going to have those low and high values as well. 99% of the data will fall within plus and minus 3 standard deviations from the mean. So we know that while it's not the norm, our battery life can be as low as 0.83 hours or as amazing as 8.39 hours.
We're not yet in the analyze phase, so we won't get too deep into how to analyze this data, but we are in the measure phase, and we're talking about different ways to measure your baseline. You may be perfectly happy with the average results of your process, but it may be more important to reduce the variation to make the results less variable and more tightly clustered around the center. Or you may want to improve the average and reduce the variation. The important piece to understand at this phase is that understanding and improving variation is critical to process improvement.
We talked a little bit about the sigma measure when we were learning about DPMO and final yield. These two measures can be used to find the corresponding sigma level using the table provided in your workbook. Here we will explain what exactly the sigma measure means.
The sigma measure compares the average of your performance or results to the customer requirement. In order to determine the sigma level of your process, you need to know the average, the standard deviation, and the customer requirement, as well as our performance measure.
In our picture here, we see the average marked with the orange line, right at 4.6. Let's say that the customer requirements is 5 hours. That's marked with the red line. A customer requirement of 5 hours means that as long as the time to process the order is less than 5 hours, the customer will be happy. Now if you just go by the average and the customer requirement is 5 and the average is 4.6, so That looks like we're really good. But look at the spread of the data. Almost half of the time, our orders take longer than the 5 hours that the customer requires. An important thing to remember is that customers don't feel the average, but they do feel the spread. To determine the sigma level of this process, let's just try to estimate it visually. The question is, how many sigmas or standard deviations can you fit between the average and the customer requirement? Let's drop our standard deviation or sigma lines on our chart. It's definitely less than half of 1 sigma. So we can estimate just using our eyeballs that this process is less than a 0.5 sigma process.
Now let's say that the customer requirement is 8 hours, meaning that as long as the order is processed in less than 8 hours, the customer is happy. How many sigmas are there between the average and the customer requirement? Almost exactly 3. So this is a 3 sigma process. A 3 sigma process means that almost all of the data falls within the customer requirements. Just a side note, you might be thinking, hey, all the data is within the customer requirement. And you're correct. However, statistically, there's a 1% chance that in this scenario, there could be a data point outside that 8-hour max.
One more example. Let's say that the customer requirement is 12 hours. What's our sigma level then? Well, how many sigmas fit between the average and the customer requirement? 6. This is a 6 sigma process. This process has a 99.9997% chance of meeting customer requirements. So we've covered all of the common baseline measures, and your head should be full of calculations and numbers by now. So good luck. If you need to, go back and listen to this again.
Here's a table that summarizes the measures that we just walked through. And on the column headers are some helpful hints for when to use these measures. These aren't hard rules, but this table is meant to be a quick reference to help you to decide which baseline measures are best for your project.
And a quick one-page lesson on common baseline measures. You'll find each calculation here as well as the measurement selection table.
And a one-point lesson on determining sigma level using DPMO or yield calculations. We've covered portions of this table up till now, but this is the full table. We'd read this to you now just to be thorough, but it might be slightly quicker for you to take an Ambien. Pause the video now and review your notes so that you can ace the quiz on statistics and measures.
Good luck! It has been our sincere pleasure being with you through this part of the training, and we thank you for your dedication to creating a better workplace and an environment that you can truly enjoy.